All right. So I'm muting the stream because I guess I was maybe listening to the wrong stream or something. Anyway, so hi everyone. My name is Ludovic Courtès. I'm really happy to be here today because I'm also a research software engineer at INRIA, France, in Bordeaux. So I think what you're doing here is a great initiative because as research engineers, we're in a great position to to try to help science become more reliable and more reproducible. At least that's what I'm interested in. And so, yes, I'm going to talk about reproducible research today. I'm a developer, so I'm working on primarily on a tool called GNU-Guix, which I'm going to talk about in a few minutes. So that's my perspective. And I'm also working at INRIA with high performance computing people. With an interest in reproducible science. So that's for my background. So let me see, I'm going to share my screen. Okay. So I want to talk about the role of software deployment in reproducible research, which I think is often overlooked. So let me start with a bit of background. So first of all, as you know, reproducible science has become a hot topic, and a lot of progress has been made over the last few years. So this is an example of the kind of progress I'm talking about. This is from the ACM, which is the Association of Computer Machinery, which takes care of publications in computer science mostly. They have designed a process with batches that allow them to to tell whether a given piece of software has been evaluated as itself and is reproducible. So you not only publish a paper, but you can also have software that accompanies the paper, and the ACM evaluates that software. So we're making progress towards reproducible science compared to a previous situation where we would have papers with either no software associated with it or unevaluated software, which was kind of a problem. And then we have initiatives like the ReScience Journal. So maybe you've not heard about it. It's not super famous yet. It's been founded by colleagues of mine. And it's about basically taking existing publications and trying to reproduce the scientific results in that publication. So you take the paper, you try to reproduce the results, and for that you typically need to be able to run the code. So you need to have access to the code, you need to be able to run it or to re-implement the code as described in the paper. And from there you can say, well, I'm able to reproduce those scientific results, or I'm unable to get those results. I get different results, for example, and that makes science much more robust. So wait a minute, I should actually take a look. Right, so maybe, yeah, I take a look from time to time to the to the Jitsi page, because otherwise I don't know if somebody is talking to me. All right. So this is, to me, this is the grail. This is what we're aiming at, right? Being able to reproduce scientific results. But so far, the situation is a bit different. So this is a paper from a few years back, but I'm pretty sure it's still, the conclusions still pretty much hold. The authors took a number of papers from high-profile conferences, like, so they took 601 papers, which we see on the left side. And from there, they just try to get the code that the paper is talking about and to compile and run the code. And so we have the input to the left, the number of papers, and to the right we have the number of papers for which they actually managed to just get the code and build it. And as you can see, that's a small fraction of those papers for which the authors actually managed to get the code and to build it. I know it's not super ambitious. They were just trying to build the code, not even to run it, not even checking the actual results. But still, that's a real challenge, and that's essentially where we are today. And so we need to do something to address this. There's a problem here. And so if we look at the big picture, on one side of the spectrum, we have the initiatives like the ReScience Journal, which is about being able to reproduce scientific results. And on the other end of the spectrum, we have initiatives like Software Heritage. So I don't know if you've heard about it. Software Heritage is essentially a source code archive for scientific software, but not just scientific software in general. Free software in particular, and it's about just archiving all the software that's out there, essentially. So it's a very ambitious project, but if we don't have that archive, then obviously we're never going to be able to reproduce scientific results which depend on software. So it's a key project. And then in between, so if we have the source code on one hand and we have the papers on the other hand, we need to be able to actually build the source code, deploy it, and run it. And so this is where Guix comes in, as we are going to see. So Guix is a tool that we hope will help, well, already helps actually, take software and deploy it in a reproducible fashion, even if you're going to deploy it later, like months or years after the paper has been published. So it's like the missing link, so to speak, in that big picture. So there are other things not shown on this picture. For example, when you have scientific papers, very often you have associated data, and obviously that data needs to be available as well. And so there are projects like Zenodo, which are taking care of data very well, I think. And so I'm not mentioning it because I'm focusing on software deployment, but obviously that's a key aspect of being able to obtain reproducible scientific results. All right, let me see. Yes, all right. So this for the introduction, about reproducible science. I assume people are familiar with it. I should say that, like I told you, James, if people feel like asking questions while I'm giving the talk, please don't hesitate, and James can let me know, and hopefully I can answer live instead of waiting the end of the talk. I can also take questions at the end of the talk. It's always fine. All right, so like I mentioned before, I work with high performance computing research teams. And you would think that HPC is cutting edge because, we have this vision of HPC being, top notch and everything. But when it comes to software deployment, it's not really that good. So I assume people in the audience may be already familiar with tools that you typically find on HPC clusters. So one of them is called modules. So it's a venerable tool that's been there forever. And you do module load GCC / some version, for example, and it loads a specific GCC version and so on and so forth. So it gives users a lot of flexibility about their software environment, which is crucial when you're willing to, to run your experiments on the cluster. So it's very nice, but all these modules are they vary from one cluster to another and from time to time. Like if I log into the same cluster in 6 months, well, maybe the module I used 6 months ago has disappeared, or maybe it has changed in some way, and I no longer get the same software environment. So it's not great from a reproducibility viewpoint. So then there's a number of projects that have been trying to address these issues. So trying to get more flexibility for users, HPC users, and trying to get some form of reproducibility between clusters. So you may have heard of SPAC, Conda, or EasyBuild. So EasyBuild is actually developed in Belgium, so you've probably heard about it, I guess. Conda is probably the most famous one. So all these tools are package managers, which means they allow you to install software in simple commands, with simple commands, and it's very flexible. SPAC in particular is very flexible. Well, EasyBuild as well, I guess. They allow you to deploy software very quickly on a cluster. You just log in, you run SPAC install, for example, and that allows you to install the software of your choice. So it's very nice. It's an improvement over modules, but without going into the details, those tools suffer from a certain lack of reproducibility, which means that inherently these tools rely on what's already available on the cluster. So what that means in concrete terms is that software may not build on your cluster, for example. So this is, just to give an example, this is a number of issues from the SPAC project, I think. These are just issues about build errors. So you choose a given package and you try to build it with SPAC on a cluster, and on some cluster it works and on others it doesn't even build. And this is because inherently these tools rely on the host Linux distribution on the machine. And so that inherently limits reproducibility. Right, so this is also an example from Conda. Like if you try to deploy the same software with Conda a month later, well, probably it doesn't work, which is kind of a problem because, many people view these tools as helpers towards more reproducible science. So that's the first approach people have been following. And the second approach is to preserve the mess, as my colleague Arnaud Legrand calls it. I'm sure you're familiar with that approach. So it's containers, right? So there are several tools for containers. One of them is Singularity, which is nowadays quite popular in HPC. Singularity is roughly like Docker, which you've probably heard about. So essentially the way it works is you define an image, you specify how to build that image, what software you want to have in that image, and then you get that image, the actual bits containing all the software that you need. And this is great because then you can share those bits, you can share those images, and people can run the exact same software. So they can, they get the exact same software environment as you have. And this is great. But fundamentally, containers a la Singularity or Docker lack transparency. So what I mean by that is that if you have a Docker file or a Singularity dev file, then you can't really tell what's inside of it. You can't really tell what the image actually contains in terms of software. So let's take an example. This is a Singularity dev file, which is sort of equivalent to a Docker file if you've ever used that before. And as you can see, the dev file starts by defining a base image, which is in this case Ubuntu. So the base image itself is already a big opaque binary blob containing lots of software packages. And from there, you run apt-get update, apt-get install, you install more software, maybe you run pip install if you want to install Python software, and so on and so forth. And the problem with that is that, well, first, it's kind of opaque. You can't really tell what's inside that big Ubuntu binary image. Plus, this recipe itself is not reproducible. So for example, the result of running apt-get update will depend on time. Like if I run apt-get update today, well, obviously I won't get the exact same collection of software packages than if I run it 6 months from now. So that's a problem because just looking at this dev file, I can't really tell what the resulting image is going to contain. And so this is where Guix comes in, and in particular the Guix-HPC project. Right. So the Guix-HPC project is about trying to benefit both from the package manager approach that we see in SPAC, easy build, and so on and so forth, and from the reproducibility aspect that you get when you use containers like Docker, Singularity, and all these tools. So we're trying to get the best of both worlds. Where's my, yeah. All right, so GNU-Guix itself is GNU-Guix is the tool itself, which is roughly a software manager, software deployment tool. We can call it in many different ways, as we'll see later. It started in 2012. There are like 15K packages nowadays, lots of scientific software packages, in particular bioinfo packages. I think there are quite some bioinfo people in the audience, so we can discuss it later if you want. In 2017, we started the Guix-HPC effort with several research institutes, where the goal is really to be able to focus on HPC needs. So HPC is taken in a broad sense. So it's about focusing on the needs of cluster users and HPC users and all that. So that's a rough introduction. And oh yeah, and there's a 1.2 release coming soon, like in the following days, if everything goes well. We'll see. So just to give you a feel, I'm going to show a few command lines. It's a bit geeky, but well, we're engineers, and probably you're used to typing this kind of commands. So I feel like it's important to get a feel of what the tool looks like. So like I said, essentially you can view Guix as a package manager. So there's a Guix install command, there's a Guix remove command, there's a Guix upgrade command, and all that. You won't be surprised. So for example, the first command here installs GCC, OpenMPI, and the hardware locality package. The second command is probably less common. So I don't know if it's the same for you, but I'm always struggling with environment variables. And so what that second command does here is define the right environment variables to use the package that I just installed. So in this case, for example, I installed GCC, and for example, to find its header files, GCC needs the C include path variable to be set correctly. And so this command is going to take care of that. And the same goes for Python packages. If you install Python stuff, then it's going to define the Python path variable appropriately. And this is pretty nice. What's less usual also is the third command that we see here. Basically, you can always roll back. So every time you install or upgrade or remove packages, it's a new transaction that you make. And so if something goes wrong, you can always say, all right, roll back, and you get the exact same software install that you had before that transaction. And the last example here is, it's a bit like virtual env for Python, if you've used it before. So it spawns a development environment containing precisely GCC 5.5 and HWLock version 1. So it starts a new shell where you have all the environment variables defined to use these two software packages. So it allows you to create, one-off software environments where you can, hack on your own software or experiment with specific pieces of software, things like that. So far, so good, but sometimes you want to collaborate with other people, and to do that, it's even better if you can just declare in a file what exactly you want to have in your software environment. So in this example, I'm just creating a mypackages.sem file that contains the specification that we see below. And these 3 lines actually say, well, I want an environment that contains GCC toolchain, OpenMPI, Scotch, mums. And so if I run that command, it's going to install precisely those 4 packages. So I can have that file under version control, I can share it with my colleagues, and they can immediately deploy the exact same software environment, which is pretty nice. Now, if you look at this specification, I'm not specifying here the version of GCC that I want, for example. I'm just saying GCC toolchain. So it's going to pick the latest version of GCC toolchain that's current. But obviously, if I run it 6 months from now, I have the same problem, the same kind of problem that I mentioned before, which is that, well, the latest GCC in 6 months will be maybe GCC 11, whereas now it's GCC 10. So this specification in itself is not really enough if I want to reproduce the exact same software environment. And so for that, I need an additional piece of information, which is the revision of Guix that I'm currently using. So Guix itself is both the tool and the package collection. So if I run Guix describe, it's going to say, well, I'm using this revision. It's this Git hash that we see here. And this revision itself describes precisely the revision of Guix and of the whole package collection that I'm currently using. So with this piece of information, plus the manifest that I described before, I have enough information to reproduce the exact same environment. And from there, I can take that description. So we have, for example, we have Bob on his laptop. Bob can take that description with the revision hash here, and Bob can pass that hash to Alice running on a supercomputer maybe later in time, and Alice can just say gixpool -- commit that particular commit ID, and from there Alice can deploy the exact same environment using Guix package -- manifest. So this is a key aspect from a reproducibility standpoint. So essentially, it means that Guix allows you to travel in space, so from one machine to a different machine, from your laptop to your HPC supercomputer, and in time. So that means that you can restore the exact same software environment even 6 months from now, maybe, and that's going to be fine. Guix is taking care of making sure you reproduce the exact same environment. And unlike what we've seen before with Singularity, we have here a detailed description of what the software environment contains, right? It's not opaque like a Docker file could be. All right. So I'm still, getting used to giving talks online. It's always a bit of a real experience compared to talking in front of an audience. I have to imagine what people are thinking. I hope everything is all right. Okay, let's see. All right, so because I'm talking about traveling in time and space, obviously, someone eventually came up with a Guix time machine command, which allows you to do time travel in a single command. So for example, with this command, I can travel back to the given commit, and using that commit, install the hello package, all in one command. And this is, very convenient. Like if you're writing a paper, for example, you could very much insert that information in the paper. You could very much insert the specific revision that you use in the paper along with the manifest maybe. And if you share that information in the paper, then reviewers can redeploy the exact same software environment. So this is what a Guix package definition looks like. So obviously you need, at some point, packages need to be defined in Guix, right? There are 15,000 of packages right now in Guix proper, plus additional third-party channels. But people have been working on defining on those packages. Perhaps you'll have to define yours as well. So what we see here is that package definitions are essentially, what you would expect from this kind of tool. So you describe the home page, the name, the version, stuff like that, and you specify where the source code itself is to be fetched. So in this example, we say, all right, I'm going to fetch the source code over Git, and I need this specific commit. All right, and I want to perform a recursive checkout. And the interesting bit here that we're also specifying the hash of that checkout, right? So we explicitly state that the source code I intend to be using has precisely this hash, this SHA-256 hash. And so that means that the package definition is very clear about what its expectations are. And if for some reason Git would give us a different checkout, then Guix would error out and say, well, look, I'm not getting the right source code, so I'm not going to build that package. Something is wrong. So essentially, you could view Guix as a source-based distribution, sort of like Gentoo or even Spark or EasyBuild if you're used to these tools. And that's fine, but like I said, we want to be able to travel in time. And obviously, if you look at this definition, there's a potential issue here, which is what happens if the Git repository that we're referring to here vanishes. It's always a possibility that happens. And so this is where software heritage comes in. So in Guix, we have integrated support for software heritage, which means that when you try to build that package, so if everything goes well, you get a pre-built binary directly and nothing gets built locally. But if pre-built binaries are not available for some reason, then the package itself is going to be built locally. But for that to happen, obviously the source code needs to be available. So Guix will first try to look up the source code at the URL that we've put in the package definition here. And if that fails, then Guix automatically falls back to using software heritage. So it basically goes to the software heritage archives and asks, do you have commit 2F30, blah, blah? And then if software heritage has that commit, well, it's being automatically, transparently downloaded from software heritage instead of the original website. So this is very convenient. It gives us more guarantees that we will actually be able to reproduce software environments in the future. It's not the end of the story either, because of course we need to ensure that software heritage has good coverage of all the software that we use in Guix. And so we've been working with software heritage to be able to tell them what they need to archive so that our packages are completely covered and archived in the archive. All right, so I've been talking about how to use Guix just to give you a quick idea of what other things Guix can do. So one problem we faced in HPC is that obviously, most supercomputers do not run Guix yet. Hopefully that will happen later, but at this point, when you log into a supercomputer, chances are that Guix is not available. So one thing we needed to be able to take advantage of Guix on those machines is the ability to export basically packages in a form that can be consumed by those tools, by those machines. And so the Guix-pack command can produce a bundle, an application bundle that contains precisely the packages that you give. So in this example, Guix-pack will create a tarball that contains Python, NumPy, and SciPy. And it's a self-contained tarball, so you can use it on a different machine. And what's even more useful is to create a relocatable tarball, what we call a relocatable tarball, which means that it's a tarball, an archive that you can extract on the cluster, and it's going to just work basically. So then in this example, you would run ./bin/python, and it should just work. So there, If you're curious, we can discuss it later, but essentially we're using user namespaces or some other tricks that make binaries relocatable. And if you're targeting a machine that has singularity, you can also export your application bundle in the singularity format. Or if the machine has Docker, you can also export in the Docker format. So you get nice interoperability with all these tools. Which is kind of ironic because I said bad things about containers before, but I think containers are useful as the runtime side of container is a useful tool to share pre-built binaries, and that's what we're doing here. One last thing, Guix, manipulates dependency graphs of packages, and since it has that knowledge, you can actually rewrite the dependency graphs. So, for example, the first example here would change the source code that's used to build the hardware locality package. So, like this is one way, for example, to test a release candidate table. And the second example here would build the mumps package, but replacing Scotch by another package called ptScotch, which is essentially the parallel version of Scotch. And so you're just rewriting the whole dependency graph, and every time you see a node for Scotch, you replace it with ptScotch. That's what this command does. We call these options package transformation options, and there are several of them. You can check the manual, and it's pretty handy. And if you need flexibility in your software environments. All right. Yes. So let me go on. So the message here is that reproducible deployment is the key here. If you're interested in reproducible science or open science, as they say, I heard it's Open Access Week, by the way, so it's a good time to discuss these topics. So if you're interested in reproducible science, well, I think a prerequisite is to have reproducible deployment. So let me give a few examples of how we actually take advantage of Guix in a scientific context. So this one is an article by colleagues of mine, friends of mine in Berlin in bioinformatics, where they essentially use Guix to provide fully reproducible genomics pipelines, which I think is quite unusual. So what they did using Guix is that they managed to define all their pipelines using all these different pieces of bioinformatics software, and to have this pipeline entirely reproducible. So bit for bit, the whole, every software element of the pipeline is reproducible, and the whole pipeline, the pipeline as a whole, is also reproducible. So it's a very high degree of reproducibility. And I think it's important to be able to go this far, right? Because, bit for bit reproducibility is something we can actually check for, and it's the only way that we can effectively verify that we're talking about the same pieces of software, right? If I have bit for bit reproducible software, then I can verify that the one you run is the same one as the one I run. And that gives, again, more strength to the conclusion that you draw from your software experiments. After this work, people in Germany and in the Netherlands came up with a prototype that's called the Guix workflow language. So in bioinformatics, you're probably used to using some workflow language. The common workflow language, CWL, is the most common one. From what I heard, I'm not an expert in this area, but that's my understanding. There's also SnakeMake, things like that. And the idea for the Guix workflow language was to try to have both reproducible deployment, well, to have reproducible deployment built in the workflow language itself. So why did it matter? Well, when you're describing a workflow, you not only want to say which commands need to be run, you also want to say precisely where those commands come from. And so the insight here was to say, well, if we really want to fully describe the workflow, we also need to describe how the software that's used in the workflow is used, right? And so with the GWL, you can describe a workflow, so a pipeline like the one we see on this slide, where you say, for each node, you specify the software that's being used, and that's itself a Guix recipe, a reproducible recipe. That also specified the command that you actually run, the data that you take in, and the data that you produce. So you have a workflow language, but that's deployment aware, so to speak. Another experiment that we've made is Jupyter integration. So as you probably know, Jupyter notebooks are a very convenient way to work towards reproducible science, right? Because it allows you to mix narratives with actual code. And so your peers can take the notebook, run it, and just check what results they get. And they can experiment with the notebook. That's a great tool, but the problem is that the tool doesn't take care of software deployment. So for example, if you take a Python notebook, the notebook itself does not specify which pieces of software it needs. It does not specify which Python version it needs. It does not specify which libraries it needs. So it's not self-contained. And what we did with Guix-Jupyter is that we defined what they call a kernel for Jupyter. And when you use that kernel, you can specify an environment. So within your notebook, you would add those Guix environment annotations that allow you to say, well, I want to create a matplotlib environment, and that environment should contain those packages. So IPyKernel, IPyWidgets, and matplotlib. And from there, the kernel automatically builds that environment containing precisely what you asked for. And from there, you can run your Python code, and you can be sure that it's running in the right environment, using the right Guix revision. You can also specify which Guix revision you want to use. And so you get a self-contained, reproducible notebook. So that's still at an early stage, but that's the kind of thing we want to work on. Another experiment that we did was in the context of the 10 years reproducibility challenge. It's an initiative that was started by ReScience. So essentially the idea here was that you take a paper that you wrote 10 years ago or even more, and you try to reproduce the result that appear in that paper. So software-based results. And so I took on that challenge, which turned out not to be an easy task because, you know, I first had, like everyone else, to find the software that I used in the paper that I chose, and then try to build it and so on and so forth. And building it typically requires having access to software from 10 years ago as well. And so, well, you can look at the ReScience page here, and you'll see that everyone who participated had to deal with these problems. What I did here is a bit different, trying to come up with a reproducible pipeline that goes from source code to PDF. So usually when you write a paper, you have the source code at one end of the spectrum that leads to an executable, and then you have data, you have a text file, and you take all that and eventually create a PDF, right? This is great, but the problem, if you look at that picture, is that it's not self-contained. There are missing bits here. In particular, to go from source code to executable, you need libraries, you need a compiler, stuff like that. And so using Guix, what I did for the paper I chose was to actually define everything. So instead, I have, all the details. So I can say that, to lead to that executable, I need at some point maybe GCC. GCC itself is built from source. I need Python, which depends on GCC. Python is also built from source, and so on and so forth. So I ended up writing a definition in Guix that describes the whole pipeline to go from source code to PDF, essentially. And it's entirely self-contained. And it's reproducible because, like I've shown before, you can travel back at the right point in time. So I saved the output of Guix describe. And you can, using Guix Time Machine, you can run the whole pipeline, and you can be sure you're using the exact same pieces of software than the one I used. So you can see the result here. That's a paper I published for ReScience. It describes the whole tooling that's used. So it's kind of a proof of concept. It's the first time we actually try to use Guix all the way down, to produce a paper. But I think this is what we want to aim at if we are to provide tools for reproducible research. And from there, I would like to, to create libraries and high-level tools that researchers could use for their articles. Like if you're using LaTeX or if you're using R Markdown, for example, stuff like that. If we could provide libraries that allow you to easily, define the whole pipeline that leads to your paper, to your final PDF, then I think we would have a tool that really raises the bar in terms of reproducibility. All right, I think it's about time to wrap up. So going back to the big picture I showed at the beginning, so we have initiatives like ReScience or ACM badges, that kind of stuff, which is the grail in terms of reproducibility, reproducible research. And at the other end of the spectrum, we have software heritage, which is the universal software archive. And so Guix is trying to bridge these two things by providing reproducible software deployment. And I think reproducible software deployment is crucial if we want to actually have reproducible research. It's not the only thing that we need, but it's definitely a prerequisite if we want to build reproducible research. So Guix itself allows you to deal with packages. You can call it a package manager if you want, but it also deals with environments, like with the Guix environment command that I showed before. It can also produce container images, so you don't need separate tooling, non-reproducible Docker files and stuff. Guixpack can create it for you. And something I didn't show here, that Guix can also take care of complete systems. So you can, just like you would describe a software package, you can also describe an operating system configuration, and Guix can deploy it on the bare metal. It can also create virtual machine images, Docker images, things like that. So to summarize, I think as a research engineers, I've been at INRIA for a bit more than 10 years now. And since when I started at INRIA, I've seen more and more research teams start using version control, for example. So in the early days when I was at INRIA, many research teams did not use version control. So you've probably experienced this as well. They would use very ad hoc tricks to save versions of their code and to share it among themselves. But I've seen, we've done training sessions about version control, and people more and more got used to, using the right tools. So using version control tools like Git. And it's getting better. And I think, now most research teams know that they should use Git and know why they should use this kind of version control tool. And I think just like we managed to get research teams, I mean, we, in a broad sense, obviously, it's not just ourselves at INRIA, but I think it's a general trend. And just like we saw that trend towards using version control tools in academia, we should go forward and promote reproducible deployment and make it a best practice. So I think tools like Guix should be, a standard way to come with reproducible deployment. And non-reproducible deployment should become a thing of the past in research. That's my hope for the future. And this is it. Now I'm happy to answer any questions you may have. Yep. All right. So let me see. I cannot hear you yet. I'm trying to tune in on the stream. Yes, James, can you give me the URL again? I don't know. Maybe I'm looking at the wrong YouTube URL because I can't hear you. So, all right. So there's a yes. Sorry, I still can't hear you, but at least I can read the question that you typed in, James. So, okay, now I should have the right URL. Let me see. And then I'm going to answer the first question that we have. Okay. So, the one question is, what would be the advantage of Guix environments over Conda environments? Yeah, that's a question from the chat, I hear. So, well, so Conda environments are, nice and flexible, but they're not reproducible. So I should also say that I'm not an expert in Conda. I'm more familiar with SPAC, for example. But the thing is, you cannot generally assume that Conda will be able to reproduce a software environment in the future. That's one thing. And the other thing, I think, is that Conda does not have reproducibility built in, so to speak. So with Conda, you retrieve pre-built binaries, but you cannot rebuild them yourself. And Conda does not use the kind of techniques that we use in Guix to ensure reproducibility. And in particular, in Guix, we use isolated build environments. So every time a package gets built with Guix, it's built in an isolated environment, which means that we can be pretty sure that the build result is deterministic, right? Well, reproducible. And so that's a key difference compared to Conda. Also, binaries in Guix are not central like they can be in Conda. So you don't need to rely on some archive of pre-built binaries, because you can always, come back later in the future and just rebuild everything that needs to be rebuilt. So if you have pre-built binaries, that's fine. You're saving time. You don't have to burn CPU time building things. But if you don't have them, that's also fine. You just need to build them. And since everything is designed so that those builds are reproducible, that's okay. That's completely equivalent, Using pre-built binaries is completely equivalent to rebuilding by yourself with Guix, because precisely builds are reproducible. All right, so I see the second question. So are there any deployments of Guix on current HPC systems? Yes. So if you look at the hpc.guix.info website, in the About page, I think, there are several HPC systems listed there. So I can tell you, for example, that the cluster we use, so the research teams use at INRIA Bordeaux, definitely has Guix on it. It's a relatively small cluster though, but there are bigger clusters using it. In France, there are a few clusters in France, what we call regional clusters. So, there are several tiers of clusters in France. I guess it's the same in most countries. So the top tier, so the national clusters, there are just a few of them. They do not use Guix, but there are a few of the next level, the tier 2 clusters, I think it's called, the regional cluster that use Guix. And then in Germany and in the Netherlands, and I think Australia and the US, we have a bunch of clusters using it. The next question is Guix difficult to install and start using? Where should I go to learn more? So to learn more, you can visit the Guix homepage, I guess, so at guix.gnu.org. It's not difficult to install, so we provide a script that can install it on your laptop in 5 minutes. Basically, essentially it needs to download a pre-built binary of Guix, a self-contained binary, and then to start the Guix build daemon. Yeah, that's about it. So it's pretty fast, and you can run it on your laptop very quickly. If you want to deploy it on a cluster, it's a bit more complicated, because on a cluster, obviously, you have to choose how build nodes are going to interact with the head node of the cluster, for example. So there's an article on hpc.guix.info on that part. But on a laptop, it's really easy. Where can I go to learn more? Well, so if you look at guix.gnu.org, there's a help page that links to manuals, which are translated in several languages. There's also a reference card, and the manual now has a getting started section. I don't know if I can show it from here. So that the getting started section is designed precisely to make it, well, easier to get started, as you could guess. Right, let me see. Right, so this is the getting started section I'm referring to. So it gives you the main command that you need to know to get started, basically, and with links to, additional information if you want to go further. All right. Yes. So the next question that we have here is, can I install it on Android on ARMv7? I think so, yes. So you can install it on any system that runs a Linux kernel, of which Android is one example. And like I mentioned during the talk, Guix supports 32-bit ARM, so it's possible. I know there's a blog post actually from maybe 2 years ago on the website that mentions running Guix on a phone, which is kind of weird, but it's possible. It's probably going to be a bit slow, because these CPUs are typically not very, don't have very good performance, but yeah, that's something you can try. It's definitely possible, at least. So next question. I have a dependency on a particular OS API. Does Guix help me reproduce software that run on old Linux? So it depends what you mean by old Linux, because Linux is just the kernel of the operating system. So it's not the whole thing. So I usually, one of the reasons I use the term GNU Linux to designate the whole operating system is to avoid confusion, because Linux is just the kernel. And it's very unusual for applications to rely on specific APIs of the kernel itself. Usually you rely on APIs of the C library maybe, or some kind of library, maybe OpenSSL, whatever, but not the kernel itself. And so in Guix, when you have a package definition, that definition basically describes the whole dependency graph of everything, of the whole application recursively. So it also describes how to build the C library that the application uses, how to build the compiler that the application uses to build itself, and so on and so forth recursively. And so yes, you can move to older software stacks, user-learned software stacks in general. Now the thing is that Guix was created in 2012, so if you want to move, to older software stacks, then you need to make an extra effort to actually define packages for those old versions that you used back then. And one thing we did, so I mentioned the 10 years reproducibility challenge of ReScience. And one thing I had to do for that challenge was to define packages for old versions that were, more than 10 years old of software I needed for my paper. And so we created what we call a channel. So in Guix parlance, a channel is a collection of packages that you can provide in addition to those packages that Guix already provides. And so we defined the Guix past channel, which contains old versions of a bunch of software packages. So if you look up Guix past on the internet, you should find that channel. And it contains, for example, Python version 2.4, which is an ancient version of Python. But it's useful typically if you want to be able to reproduce old experiments. I see there are more questions coming up. Yeah, so I think we're about done, right? Yeah, it's about time. So thanks for having me again. And maybe we can talk again later, and you can join the Guix channel, the IRC channel, or the mailing list. There's a Guix Science mailing list in particular that people in the audience may be interested in. If you want to discuss your particular use cases, we'd be interested in having you there. Thank you. All right. Bye-bye. Bye.